Okay, recording. And so it's a pleasure to introduce Alex Zupan. And to be honest, I blanked on your title.
It's all right. I have it here.
Here it comes.
Here it comes.
We'll talk about characterizing handle ribbon knots. Great. Go for it, Alex.
All right. Well, thanks very much for the invitation, Dave. It's nice to see some familiar faces here. I don't know. Giving these talks is bittersweet because I realize how much I miss everybody. But it's very good to see you all. All right. So first, I'll say that this is joint. Okay, we got all our settings right. This is joint with Maggie Miller. And I want to pontificate about the slice ribbon conjecture and this class of knots in between it called handle ribbon knots, or as Jeff and Kyle would call them, strongly homotopy ribbon knots, right? All right, so let's start with ribbon knots. I got a little bit of background just in case there's some uninitiated folks here. So the first definition, KNS3 is ribbon if it bounds this immersed ribbon disk. Bounds an immersed ribbon disk D in S3. I think this is the least useful definition of a ribbon disk, but it's the one we always use because it's easiest to show the picture to someone who's not a topologist or not a three-manifold topologist or whatnot. So here I've got an STL file. I'm going to stop sharing immediately and show you this. This is my cool technology of the talk. There you go. Can you see it? So there's a lovely ribbon disk for the square knot. I wish I could claim that I made this. I hired an undergraduate to teach me how to use a 3D printer a couple summers ago. And Andy Loken made this for me and then printed it. And if you've been to my office, you've seen the nice print. So there is a ribbon disk. It's got two ribbon singularities. And we won't spin it around again, but I got a copy of this that I'll bring up a couple more times in my talk. There's your picture of a ribbon knot though. Much better than I could draw with my stylus. Hopefully my screen comes back. Oh yeah, I don't know if I want to jinx this or not. I gave a talk at Western Washington a couple weeks ago and my computer quit. It just died right in the middle of it. It took me about 4 minutes to get back on. This happens occasionally, but never before during a talk. And I've also never prefaced a talk with this. So we'll see if I jinx myself. The computer's like it's on its way out. It's starting to show signs.
Happens, we'll just stick around.
Okay, yeah, good. I don't think it will, but good, okay. All right, so that's what a ribbon knot is, but the more useful definition, so equivalently, we have an embedded disk, so K bounds embedded disk D in the 4-ball, such that, I'm not gonna write out what this is, but this is the radial height function emanating from the center. If I look at the restriction, not to B4, to D, I can perturb that disk so that the radial height function is a Morse function on the disk. And we require that this has only minima and saddles, but no maxima. And in case you are not happy that these things are equivalent, let me draw a picture. All right, so there's our ribbon disk. And what can I do? Well, near each of these ribbon singularities, I can attach a little band. So there's a band, and it's kind of hard to see because I picked a different angle here to use later, but I'll attach two bands. And the bands are perhaps contained almost entirely within the ribbon singularities, and then I can resolve those bands. And I get an embedded disk, and the schematic looks like the following. Here is my knot that I started with, K, the square knot. And then the bands describe a cobordism. Let's see. To a 3-component link. Here are my schematic drawing of the bands.
So those bands are are rectangles embedded in your ribbon.
There are rectangles embedded in the ribbon, right? Let me
from one side
draw a better picture of the band.
Which rectangles are you?
I'll draw a better picture here. Let's do some gray.
Just cutting. He's just cutting the ribbon.
So here's my surface. Let's make it purple. So there's the little ribbon thing that goes through another sheet of the surface. So here's the other sheet of the surface. And the band is a rectangle that is contained close to the ribbon intersection. And then resolving the band gives me the following picture. So this is the band resolution. And it's straightforward to check that when I do these two band resolutions, I get a 3-component unlink. And so the two bands give me this cobordism in B4, and then the 3-component unlink can be capped off with 3 disks. And so this is my embedded ribbon disk in B4. And I did not do this efficiently. I could have just used one red band and the whole thing would have fallen apart. But I wanted to show you general construction. You take all of the ribbon intersections and put bands at all of them, and you will end up with an unlink. And so that is an alternative definition of a ribbon disk that I will use going forward. Okay, any other questions? All right, so let me define, so here's, my talk has 2 parts. So part 1 is a characterization of handle ribbon knots with derivative links, and part 2 involves Morse 2 functions. So let me define a derivative link. So let F be a Ciphered surface for knot K. Sometimes a derivative link is also called a metabolizer. A derivative link L. It's contained in the Ciphered surface F. For K, let's see, is or satisfies these 2 conditions. So I require that if I cut the surface F along the link L, this is connected in planar. So the number of components has to be the same as the genus of the surface, and they have to be linearly independent in first homology of the surface. And then the second condition is that the linking numbers of components, and this is a positive push off, this is equal to 0 for all I and j. So another way to say this is that all of the pairwise linking numbers are 0, and in addition, the surface framing in L is the 0 framing. So that's the definition of a
link is embedded in the surface.
It is contained in the Ciphered surface, yes.
So the only reason to do the push off is for when I equals j.
Right, yes. The only reason you need the push off here is when I could say that linking numbers are 0 when I is not equal j, and surface framing of each component is 0. Yes. Okay, so that's a derivative link. What's the relationship between this and ribbon knots? Well, here's a proposition. It's not so hard to prove. K is ribbon if and only if K has an unlinked derivative. Meaning there exists a Ciphered surface for K, and on that Ciphered surface, there is an unlinked derivative. Let's show you the proof here. I need my picture back. So the angle that we're looking at this is better for this proof. So there's a ribbon knot. Let me show you the unlinked derivative. Well, I have to show you the Ciphered surface also. Let's move this over just a hair. There is a natural way to take a ribbon surface and get a Ciphered surface by smoothing the ribbon intersections. So suppose that I have, let's see, this gray sheet of surface here, and then let's do it like this. A ribbon intersection. So there's some surface and a piece of ribbon passing through it. I do this operation where I kind of flatten a piece of the knot out like that, and then cut out a little square. So here's my ribbon surface right there with the ribbon intersection given by, let's make it red. There's the ribbon intersection. Now on the lower picture, we have this planar sheet, but I've removed this little square, and now here is my surface. There and there. So I've transformed the surface with the ribbon intersection into an embedded surface with the same boundary. The boundary is still the knot, but at the cost of increasing genus.
So say once again, what did you do here?
So I've got this ribbon here, and I flatten it out so that instead of meeting the surface transversely, these arcs of the knot like have these piecewise linear, so they come straight down. There's a sub arc that is sitting flat on the surface, and then it goes downward. That's the first thing I do. So then my ribbon disc becomes like this non-transversely immersed surface with a square of intersection right there. Mm-hmm. And then I cut out the square. And when I cut out the square, I'm left with a closed surface. And I guess I have to smooth out the corners, but if I cut out the square, I get this closed surface with...
Not closed. You don't mean closed.
Sorry, embedded. That's the word I'm looking for. Thank you, Dave. I get an embedded surface whose boundary is the knot, AKA a ciphered surface.
Is that the same thing as like removing a two-dimensional neighborhood of the red arc?
Is it the same thing as removing a two-dimensional neighborhood of the red arc? Probably not.
Well, the problem is that introduces, you're thinking of like having a hole in the sheet that goes across, but then you'd have an extra boundary component. You'd have a surface with one round boundary component for each hole that you went through.
Yeah, what I want to think about, if I look at a cross section of the ribbon intersection, is I take this X cross I and I smooth it in one of two ways. I replace that with that picture cross I, basically. So it's kind of like smoothing a ribbon intersection here. Although I find this picture difficult to understand what happens when you get close to the black vertices.
I understand. I mean, ribbon disk is not a ciphered surface, and you're making like an optimal ciphered surface from it.
That's right. All right. So the forward direction of this proof, I'm not going to draw it on here, but I can ciphered surface-ize this ribbon disk, and then what I end up doing is just putting a loop around there and a loop around there. And in this local picture, I add in this curve. So for every smoothing, I put a blue curve around the square in the surface, and that will be an unlinked derivative. Any questions? The reverse direction is maybe a little trickier, but not so bad. This is the reverse direction. And so there exists a cobordism with only saddles from K to F cut along L. So maybe I should use this example again. So if I cut open along my unlinked derivative, I have my knot K. And if the unlinked derivative has two components, each of those will leave two boundary components when I cut off. And so this piece right here is embedded in S3. This is like my ciphered surface cut open. So I won't draw on the saddles, but I can get from my knot to these images, these copies of my link after I cut open. And then since this is an unlink, I can cap off with disks. Cap off. Since L is an unlink. So ribbon knots can be characterized in this way with derivatives. All right, how about slice knots? So I won't say this a bunch. I'm just going to use B for a homotopy 4-ball. And K in S3 is slice in some homotopy 4-ball B if there exists a disk D properly embedded in B such that K is the boundary of D. All right, and the famous slice ribbon conjecture says these two notions are the same. Well, combination of the slice ribbon conjecture and the smooth four-dimensional Poincare conjecture tells us that every homotopy 4-ball is in fact standard smooth 4-ball. And so if we were restricted to the setting of B4, then that's the slice ribbon conjecture tells us that these are the same. All right, and so there is a characterization, well, a conjectured characterization of slice knots using derivatives as well. So this is the stable Kaufman conjecture of Cochran and Davis. It's called this because they disproved the Kaufman conjecture, and so they proposed a stable version of it. And so the stable Kaufman conjecture says K in S3 is, they probably stated this in B4, but I'm just going to state it in arbitrary B. K is slice in B if and only if there exists, how do I phrase this over here? I'll do K has. So this is going to be like my statement of the proposition for ribbon knots, a certain kind of derivative here. So if and only if K has a slice derivative. And so this is open. One direction is straightforward. So the reverse direction is relatively easy. I will draw the same picture that I did up there. Oh, sorry, Kat wants to come in the room.
Slice derivative means each component bounds a disk in B, right?
Yeah, pairwise disjoint disks. So there's a collection of pairwise disjoint disks in B. Yeah. Yes. So yeah, not just that every component is slice, all of the slice disks have to be disjoint. So just as before in the unknot case, the picture is going to be the same. I cut open along my slice derivative. This is embedded in S3. And in this picture, I could cap off in a parallel copy of S3 in B4, but now I have to cap off, maybe I'll draw them kind of wonky to show that these might not be standard disks. But this is slice, and so I can cap off that surface with disks and obtain a disk for the knot K.
What was the original Kaufman conjecture? That's not true.
Every genus 1 ciphered surface for a slice knot has a slice derivative, or even an ARF invariant 0 derivative. So yeah, so in the paper by Cochran and Davis, they disprove that Kaufman conjecture and then show that if you stabilize the ciphered surface once, if you move up to genus 2, then in fact, I mean, all those knots are ribbon, and so they have unlinked derivatives, just not on a genus 1 surface. Okay, so we have a characterization of ribbon knots. We have a characterization of slice knots. Let me now tell you about handle ribbon knots. And here's the, let me motivate the definition before I give you the definition. Okay, so if K bounds a ribbon disk, D in B4, then if I look at the complement, B4 minus D, so I remove a neighborhood of the ribbon disk. This has a handle decomposition with a single zero handle. And the standard carving out singularities of an embedded surface gives you a handle decomposition of the exterior. You get some one handles. These correspond to carving out the minima of D, and some two handles. Those correspond to carving out the saddles, but no three handles. So it's sort of like an ambient version of the ribbon disk criteria. We're allowing some critical points, but not others. If you think about a Morse function on the exterior. And so a handle ribbon disk has this property. So, and it's also a definition that makes sense to do in an arbitrary homotopy 4-ball. So K is handle ribbon in some homotopy 4-ball B if there exists a disk D in B such that K is the boundary of D and D, did it again, B minus the neighborhood of D has a handle decomposition without three handles. So in the interest of trying to decide whether the slice ribbon conjecture is true, one might study handle ribbon knots because we want to understand the finer distinctions, the different gradations between being slice and being ribbon. And so what I wrote above tells us that ribbon knots are contained in handle ribbon knots as a family. And handle ribbon knots certainly bound disks, which are slice disks. And so every handle ribbon knot is a slice knot. And in case you thought about these problems and have thought about homotopy ribbon knots, I won't define it, but in the middle here, this is homotopy ribbon knots.
And so when you don't mention the homotopy 4-ball B, then handle ribbon means in some homotopy 4-ball, right?
Yeah. So yeah, I could say this is all happening in B4, or I could just put in any arbitrary homotopy 4-ball B. That's right. And so ribbon and none of these containments are known to be equalities. It's all open.
Whether for B4 or a homotopy B4, or is there potentially a difference?
There is potentially a difference, yeah. So B4 equals B is the smooth 4-dimensional Poincare conjecture. Okay, so that's a handle ribbon knot. One more definition for now. I know it's a lot of definitions, but I have to do it. So L is a link in S3, is called an R-link if L has n components and the zero surgery on each component of L yields the connected sum of n copies of S1 cross S2. So it's important to note that these ends are the same. If I have such an L, I can build a homotopy four-ball. I can think of L as like a relative Kirby diagram. And so an R-link L gives rise to a homotopy four-ball. B sub L, which is equal to, take S3 cross I, union two handles along L. Well, let's do it like this, union along L, two handles. And then the boundary of that is going to be this connected sum of n copies of S1 cross S2. So we glue on three handles and then a four handle. And there are n two handles in this construction and n three handles. And so you can show that this is a homotopy four ball. All right, any questions? Dave, should I end at 250?
You can go to 3. We stalled a little bit. It's up to you, really. 255. I mean,
All right.
Past 3 is.
Yeah, I don't want to commit any grave over.
No, there's no grave error. Yeah,
that's the worst thing.
Target 250, 255. So you can see.
Sounds good.
When you get there. Yeah.
Okay, so an unlink is an R-link.
Oh, this time.
Another example here. I'm going to get as much mileage as I can out of this picture. No, not a camera. Come on. Cancel. That'd be pretty bold to take a picture of yourself and put it in your talk. All right, so if I throw on one of these derivative curves, the square knot, let's call that U. So square knot Q cup U is an R-link. And so Jeff and I have thought a lot about R-links. Is it conjecture, the generalized property R conjecture says that every R-link is handle side equivalent to an unlink. That's the case with this one, but that's open. Okay, those are R-links. Why am I telling you about them? Here's the theorem, or the first theorem. So we prove that K is handle ribbon in B if and only if K has an R-link derivative L. And as a consequence, well, I guess I should say if it's if only if R-link L such that B sub L is equal to B. So this is the handle ribbon version of the other two characterizations. The one that's known to be true for ribbon knots, right? That's an unlinked derivative, and the one that's conjectured to be true for slice knots, which is having a slice derivative. And the containment works the same way. Unlinks are always R-links, and R-links are always, I didn't write this down, but R-links are always handle ribbon in B sub L, so they're always slice. So it's another way to frame this containment, and trying to understand this distinction can boil down to perhaps understanding the distinction between R-links and unlinks, or R-links and slice links.
So this is a little different than your example above, because you're not saying K union L is the R-link. You're just saying L all by itself is the R-link. Right?
That's right. This is not an R-link derivative. No. In fact, if I drew the two unknotted components, that would be every unlinked derivative is an R-link derivative. Yeah. Okay, so how much of the proof do I want to do? Probably not a ton. Well, let's do the reverse direction. That's not so bad. Yeah, good. So, okay, suppose L is an R-link derivative for K. then there exists a sequence. This is sort of a standard argument, is that I can handle slide a knot over its derivative curves to turn it into an unknot of handle slides of K over L to get L union unknot, which is also an R-link. And so we say that K union L is stably equivalent, well, handle slide equivalent to L union unknot. And then in the handle calculus, you can cancel an unknotted curve because there's a canceling 2 and 3 handle pair. And so this is stably equivalent to just the link L itself. And so as these things can be thought of as describing handle decompositions. And so it follows that K union L is an R-link as well, with B sub L equal to B sub K union L, and then K is handle ribbon in B sub L as the core of a 2-handle in the relative handle decomposition. I'm intentionally glossing over a lot of details here, but I like to think of these handle decompositions as going from S3 inward. Instead of 0, 1, and 2 handles, I think of 2, 3, and 4 handles. And so I start with S3, I attach a bunch of 2 handles along my R-link, and then the 3 handles and the 4 handle. And so that's how the easier direction of that proof goes.
You scroll a little bit, I don't see the bottom.
All right. I will say, in the interest of time, I will say a few words about the forward direction, but this is the more exciting part of the proof. So K has this is not hard to prove, a partial R-link derivative meaning I can find a ciphered surface that contains some curves which are an R-link, but it's not quite enough curves to be a derivative because they don't necessarily cut the surface into a planar surface. And then I can promote this to a full R-link derivative with some clever stabilizations. So we use some 3-manifold topology and facts about surfaces in S1 cross S2s to find compressing disks for some closed surface coming from surgery in the ciphered surface, and that gives you a place to stabilize. And then you get more and more curves until you filled up your surface entirely, and you have your full derivative. Whew, I'm gonna take a breath. That was part 1. Oh, maybe I want to say the following, looking at my notes here. So as a corollary, we prove that if K is handle ribbon in B4, then it has an R-link derivative in B4. The R-links are sliced, and so then K satisfies the stable Kaufman conjecture. Now this is a conjecture that I've been actively trying to prove. You know, the difference between having a slice derivative and having an unlinked derivative is so great that it seems like this conjecture has to be true if we have any hope of slice ribbon being true. I guess I think slice ribbon is false, but I believe the stable Kaufman conjecture could be true. Okay, now part two. Part two involves Morse 2 functions. All right, some more definitions here. Let's see. I need to define a self-indexing singular fibration. So you have to bear with me and trust me that the payoff is good here after we do these definitions. So P is a function from a three-manifold Y to the circle, and we call this a self-indexing singular fibration if some conditions are satisfied. And let's, in the future, I'll just call this an SISF. So 3 conditions. I need P to be a Morse function. So it's a circle valued Morse function. Fibers are connected. And so only index 1 and 2 critical points. Because this is a 3-manifold. If we had a 0 or a 3, we'd have a disconnected fiber somewhere. And then finally, the index 1 critical values are contained in interval from 0 to pi, if I'm parameterizing the circle from 0 to 2 pi, and index 2 critical values contained in pi to 2 pi. So this is the self-indexing part. I've separated the index 2 from the index 1. I sort of it's directional. I start with the surface, I add a bunch of 1 handles, I add a bunch of 2 handles, and I'm back where I started. And so what is an example of this? Take a knot, K in S3, then the 0 surgery on K has a self-indexing singular fibration. So every knot exterior has this it's not fibered, but every knot is sort of almost fibered up to singularity. So there is a circular Morse function if I remove the knot with fiber a bunch of ciphered surfaces. And then if I cap each ciphered surface off with a disk, I get an SISF on the 0 surgery here. And so if the knot K is fibered, this SISF that results as an honest fibration, right? So honest fibrations are SISFs by definition because there are none of these critical points. Okay, one more, I think. We say that an SISFP taking Y to S1 extends over handle bodies if there exists some compact 4-manifold X such that the boundary of X is Y and a Morse 2 function, capital P, taking X to the annulus. I'm going to do a picture first. That looks like the following. In case you're wondering when this one would come up. You don't get to see Einstein golfing, I'm sorry. That's for my differential equation class.
Can you enlarge that a bit more?
Sure.
Thanks. I'm on a small screen.
No problem. So this is the graphic of the Morse 2 function. And do I want to actually, maybe I don't want to write down the conditions. I'll just highlight some stuff on this graphic. And so this is the function P, which is capital P restricted to the boundary of X. So on the inner S1 component, I see the arrows show the direction of compression. And so if I go this way, these are index 1 critical points, index 2 critical points. I also require that all of my radial things are directed here. So every radial line segment only crosses arrows pointing outward. Same is true for the ones that go through the braids. And then I have to have all of my cusps contained here in this capital P inverse, this pi radius. And the number of cusps n must be equal to the number of critical points n. And so that's what it means to extend over handle bodies. And again, I want you to notice that if this is an honest fibration, then the diagram is empty. So no critical points, the number of cusps is 0, and there's well, okay, sorry. It's not empty. What does it look like if there's an honest fibration? I misspoke. You have this picture and then a bunch of circles with no cusps, possibly with some braiding. And so this is what you would, this is what it means for a fibration to extend over handle bodies, is the point. If I restrict this to an honest fibration, it agrees with the already present idea you might have about extending over handle bodies. And the other thing to observe is that if I take the inverse image of any one of these radial orange segments, I get a handle body because all of my compressions are going outward. And so each one of those lifts to a handle body, although the handle bodies will have different genera as I pass through the boundary critical points. Okay. And here's the theorem. The second characterization. K in S3 is handle ribbon. If and only if there exists a self-indexing singular fibration of the 0 surgery on K that extends over handle bodies. And in sum B, and the way that it extends over handle bodies is you take the 0 surgery, you take the 0 trace and you cap off with the corresponding homotopy 4 ball. It's the same homotopy 4 ball that's present everywhere here. Let me wave my hands at a proof here. Yeah, go ahead, Dave.
Well, the Morse 2 function picture you drew on the previous slide, does that imply that that 4 manifold is a well, if the 3 manifold was S3, then the 4 manifold is a homotopy ball, or not?
Yes. Yeah. So yeah. So let's do that. Note. So we note that if this is true, if there exists this X and capital P taking X, so on and so forth, then the what do I want to say? There's this 4 ball B sub P, which is equal to S3 cross I union a 2 handle along K, and then I glue on X. This is a homotopy 4 ball. And you'll notice that being a homotopy 4 ball, if you look at this carefully, is baked into the definition. This is why I had to require that the number of cusps is the same as the number of critical points here. Otherwise, this thing wouldn't have the right Euler characteristic. And so you can, the whole idea of the proof is that you can extract a handle decomposition in much in the same way that you get a handle decomposition of a trisected 4 manifold by looking at a graphic that kind of looks a little bit similar to this. So I'll wave my hands at the proof by drawing this picture again. I'll make it as big as will fit here, Gordon.
Thanks.
All right, so one direction is easier. If this exists, then the inverse image of this is a handle body, and its attaching curves are an R-link derivative. So P inverse of 0 cross I is a handle body and a cut system is, or the boundary of a cut system is an R-length derivative. And how do you show that? Well, you have to argue that the stuff above this whole thing is a bunch of one handles. And that's, I mean, if I bend it open, it just looks like a sector of a trisection. So that's how you argue that it's, well, or three handles or whatever.
Can you read that stuff in orange again?
Yes. P inverse of 0 cross I is a handle body. The boundary of a cut system is an R-length derivative.
Mm-hmm.
So that's which direction? That is this direction. The forward direction is, well, I start with my, let me make it purple. This is my circle valued Morse function with some critical points. And so I extend this in a little neighborhood. I know it has an R-length derivative. And so I can, let's do this. And so I want to construct some two function. So there is a handle body cross I. This is from my R-length derivative.
Middle of something in 3 minutes.
And so I get this key-shaped piece. And since it's an R-length, I know that the complement is, well, it's a one-handle body. 4-dimensional one-handle body. And I cap off with the appropriate diagram. This is the standard argument in Dave and Rob's paper that a one-handle body has such a Morse 2 function. You use Waldhausen's theorem to make everything line up nicely, and it all works out. And I have to tell you about trisections. All right. So in the remaining 2 minutes, I want to tell you about the thing that is one of the more interesting things coming out of this construction, is that we get these weird.
5 minutes. I'll do.
Okay, all right, 5 minutes. This weird family of trisections. So let's see, consider X sub P, which is equal to, I take 4 ball and I glue on this homotopy 4 ball B sub P, which is defined back there. So assume that I have such an extension with this diagram. And I want to get a closed form manifold, which is a homotopy 4 sphere. And so one of my pieces, let's say X1, is just the 4 ball. And I need to decide how to divvy up the other 2 pieces. Now, I want you to think about the Morse 2 diagram. Now, instead, as an open book decomposition. With sort of a relative open book decomposition. And so we have that, P as binding K. So I have an open book decomposition of S3 with binding my knot. And then there's another function, let's call it P1. P1 is the projection to the X1 factor. So this is P projected to S1. And P1, so this has binding a handle ribbon disk D. This is a really hard construction for me to visualize. And so I don't think I'm going to say too much more about it, but all of the details are in our paper. And once we do that, we can think about lifting regions to sectors in a trisection. Let me paste this one more time. Okay, so x1 is equal to b4, not pictured. And now I have a function from the 4-ball b sub p to the annulus. And so I want to divide it here. And then let's say I want to divide it right there. And so x2 is equal to p1 inverse of closed interval from 0 to pi minus epsilon. And then x3 is equal to p1 inverse of pi minus epsilon to 2 pi. And we can prove that those are 4-dimensional one-handle bodies, and their intersections are sort of, well, the intersections will be it's tricky because this should be connected because it has the same binding. It'll be the connected sum of this surface with that surface. So let's say that, let's call this handle body h sub 0 and this handle body h sub pi minus epsilon. We get that x2 intersect x3 is equal to h0 connect sum along D, because that's the binding of the open book decomposition, h sub pi minus epsilon. And the result is let's say the genus here is equal to K and the genus here is equal to L. So it will be a K plus L genus trisection. One of the sectors is a 4-ball. The other one is genus L handle body. And the third is a genus K handle body. And I suppose if I'm being really careful, I want to make this one smaller. And no, wait, which is smaller? The third one should be smaller because it contains the cusps, and K is smaller, so it should be L and then K. Okay, here is the most interesting thing that we really weren't able to get a handle on. I can draw this. I have lots of choices when I draw this diagram. I'm using this one last time. I know I said it was the last time, but this is the last time, I promise. And this is an interesting problem to think about, I think. So I draw this arc the same, but this other orange arc, it turns out I can choose. I can pick teams like dodgeball, which cusps get to be on which team. And so I can go this way for that cusp, and this way for that cusp, and this way for that cusp. And so there exists 2 to the n choices. And which, if you make the one choice with all the cusps on one side, you get this K plus L 0 KL trisection. And if you make the other choice, you get this K plus L 0 LK trisection. And now if I make one cusp defect to the other team, I have K plus L 0 K plus 1 L minus 1, but I have different ways to do that. And I get this lattice of trisections, and I have no idea how they're related. My suspicions are a single unbalanced stabilization and destabilization. I mean, ideally, what would be great? It would be great if somehow something was happening with the topology of this, that these are all somehow a stabilization of some one underlying trisection, and that would be really useful to know. I mean, there are reasons why that can't be possible, but maybe some adjusted version of that statement is possible. And so the big question is, what is the relationship between these trisections?
And the input data for all of this is like what produces this family of trisections? It's the starting data. I lost track of the theorem.
You need a singular, self-indexing singular fibration.
Right, which is equivalent to, I'm just losing the words. So the input could be taken as a handle ribbon, not K.
Yeah.
which would then give you a self.
Right. Well, the self-indexing singular fibration isn't unique. So if you want a unique input, you would have to pick an R-link derivative, I think, for a handle ribbon knot. Yeah. Cool. Anyway, I will quit there. Thank you for your attention.
All right. Please unmute yourself and start clapping in 5 seconds after you are unmuted. Now you can. Good enough. Oh, Gordon, you muted yourself instead of unmuting yourself. Anyway, clap. Well, that was just a dress rehearsal for the real clapping after the questions. Are there any questions for Alex? One question I have, I guess, is I'll have to pick your brains a little bit after in the slower discussion time about this construction. But if you just start with a standard Morse 2 function for a trisection, so a standard trisected Morse 2 function, you also have this issue that you can't move one of the slices across a cusp unless you move another slice across the cusp. You got the 3 spokes, and you can move cusps back and forth between the different sectors to some extent.
Yeah.
And that gives you a whole family. I mean, is this essentially the same thing in that? I mean, if I were to turn this into a,
there's an issue with passing cusps through braids, though, right? I mean, it should only be in special cases that you can move cusps over.
I see. If you have simplified trisections, then
sure,
you don't have braids, and then you can move them all around.
That's true.
Yeah.
I mean, do you know anything about how those trisections are related?
No, okay. That's a project I've wanted to do and wanted someone else to do.
My intuition is that there should be a move to swim a cusp over that orange arc, and I imagine the move is like putting some swallowtail somewhere, and then canceling one cusp creatively with the existing cusp, and then the other cusp which you haven't touched is now magically on the other side of the orange arc. That's my thinking on this. But I guess I should say I haven't tried super hard to work this out. I've tried some and haven't succeeded.
Other questions? Okay, now let's really clap. Ready? 1, 2, 3, go. Thank you, Alex. So stick around. I'm going to go boil some water and make myself some tea. I'm not going to close the room. And we can chat about whatever we want to chat, social or mathematical, a little bit. And Alex, when you got to go, just go.
All right. Sounds good.
Yeah. Okay.
I'm going to grab myself some more water. I'll be right back.
Yeah.
wonder what, did Jeff give up on my talk?
I think he might teach right afterwards because usually he's ran away pretty quickly.
Oh, I see. Okay. All right.
Yeah, I actually got to go too. So thanks.
All right.
The talk, Alex. It's good seeing you.
Yeah, nice seeing you.
Yeah, if you were asking about Jeff, he has to teach right now, I think.
So in your picture, the yellow line, right? That's a three-dimensional handle body.
Yeah, that's right.
And like if you were to take the one that's on the other side of the cusp or cusps.
Yeah, I can share my screen again.
As far as like the three-dimensional things go, are they just related by a two-handle attachment, a four-dimensional two-handle attachment?
What do you mean by that?
One sec. I'll do yellow as well. So,
Alex, have you met Dan, by the way?
Yeah.
Just interrupt. Yeah, you guys have met before.
We've met before, Dan. Yes?
Yeah.
I think so, yeah. So this is some H, you called it pi minus epsilon.
Sure.
Maybe this is pi plus epsilon.
Yeah. Oh, you're asking how those are related? They are related by two-handle attachments corresponding to, like, yeah, passing radially through all of the cusps. That's right.
Okay. And so is it different to think about like this would just be a different, you attach some two handles and not others?
Well, it's sort of like where you're putting the two handles. Because they're present in the four manifold no matter what. But if I slide the thing, it's where, which sector they are appearing in.
So, I mean, you could think of, it's, I mean, the point is that the horizontal line to the, not to the right. Actually, can I back up on this picture? So if you just take this and cut along the right hand, orange line, right? And open this picture up.
Yeah.
Then you have something that then it, the folds come around. I mean, that the thing that comes in and bumps up, that's just straight across now. And you just have all the folds coming this way and all the folds coming this way. And then am I right that the new Morse 2 function you're making really is just open this all the way up, well, open it up to a third of a circle. And then the boundary is S3 with some genus G Haggard splitting on it, and by Waldhausen you just squeeze in whatever you need to there, right?
Yeah.
Yeah.
Did you just answer my question, Dave?
Well, I mean, I don't think so. I mean, I mean, I think that the Morse 2 function you're talking about is just cut horizontally and open up and then squeeze in whatever you have to make a 4-ball. That.
Yeah. Maybe this, I have to draw this picture now. If I, so maybe this, I don't know if this is quite what you were saying, but if this is X2 and the rest is X3, is that a trisection?
No, I want to, maybe I'll try and draw a picture, but it'll take me a minute. I want to plug in a little device. So that's, well, first, okay, put a dot on the left, in the middle of the left-hand side of your central black circle.
Sorry, say one more time.
Put a dot in the middle of the left-hand side of your central black circle.
Okay.
Yeah, right there. Okay, so we're in the end. You're talking about a trisection of a closed four manifold, which is the whole thing union. You know that this four manifold union 4-ball. Right?
Yeah.
Do you think that dot becomes the central trisection surface?
No, it's the connected sum of these two dots. So then you have.
Okay, let me ask you a different thing. If you cut, so that if you cut open along, okay, so the black, currently what you've drawn has one boundary, that four manifold has one boundary component, which is zero surgery on the knot. And that's what sits over the central black circle, right?
Technically now what I've switched to this open book decomposition. And so the boundary is S3.
Anyway, yeah, what sits over the black circle in the middle?
So I was abusing this diagram and using it in two different ways. Do we want to talk about the way the trisection arises?
Well, yeah. Maybe we could start.
So what sits over the black circle in the middle?
At the beginning or after he does some kind of
So right at the beginning, I had to miss it because Milenko hook up to teach his.
So for the theorem, there's the picture for the theorem and the picture for the trisection. So for the theorem, it's the zero surgery on the knot.
Zero surgery. And the red dots, the ends of those red arcs
are the index 1 and index 2 critical points of the circle valued Morse function.
Yeah, that's right. So these are the critical points of the circle valued Morse function. So like the simplest example would be something like stevedores knot. Stevedores knot is not fibered. It has Morse-Novikov number. I don't remember if it's multiplied by 2 or not. It's either 2 or 1. It has a single 1 handle and a single 2 handle.
Mm-hmm.
And it's in its simplest circular decomposition.
Okay.
And so I guess I was wondering if you just take this and cut open along the inverse image of a horizontal ray going to the right, what's the boundary now?
Oh, the boundary is a connected sum of n copies of S1 cross S2, because if I cut open, what's left is a one handle body.
So what if you take, okay, so here's another four manifold you can build. Oh, I see. No, that's just a handle body. If you just glue another handle body to it, then you're just creating connects on S1 cross S3s. Okay. Okay, so that's not a relevant part of your construction, cutting open along that per se.
Well, that's part of the proof of the theorem.
I see.
Sure.
But okay, if you so to get the open book, you then want to say, oh yeah, so how did you transform to the open book setting? What's that?
Well,
I lost that. You want to undo that zero surgery on the knot somehow, right?
That's right. So the observation is that you can take your knot and slide it all the way off across the derivative curve and cancel it. And in the process, the same picture essentially works. So let me draw the picture now for the construction of the trisection and show you how it changes. So for the trisection, above this, we have open book decomposition of S3 with binding K.
So here's one way I might imagine you're doing this. You're actually going to, I can imagine S3 as sitting over. Okay, let me ask you this. Is there now non-empty pre-image of points in the interior of that black disk?
Non-empty.
In other words, do you now have a map to a disk rather than the annulus? Once you change it, no, you're still mapping to the annulus.
Still mapping to the annulus.
So how?
I think.
Oh, have you? I mean, does S3 sit over that circle or just S3 minus K?
Oh, I want to think of. I guess it's S3 minus K. It's S3 minus K.
So you could think of it S3 sitting over the disk. If you could think of S3 minus K sitting over the circle, and then the neighborhood of the binding sitting, projecting down to the disk.
I see. So fill this in with the binding.
Yeah.
I mean, yeah, that.
Sure. So in some sense, that's undoing the zero surgery. So you go back to S3 by filling in across that disk.
Okay.
Yeah, but that's now a 3 manifold rather than a 4 manifold, right?
Right. Yeah. It's a screwed up. I mean, it's a very screwed up map because it's a 4 manifold boundary and part of the boundary maps. But if it's weird. But once you fill it, you're going to now fill in a ball somehow. So then something interesting might happen.
So the central surface is so sigma is equal to, let's call this sigma L and sigma K. Sigma is equal to sigma L connected sum along the common binding K. Sigma, that's a capital K. This is a.
The binding goes around. The binding is just one component. I see.
Oh, then those would just be 2 pages of the open book. It's not a book because it's got this extra handles in the middle.
It's like a singular open book. Yeah, but these are 2 pages of the singular open book, and they're the 2 pages with the smallest and the largest genus, because the open book is arranged so that I add genus.
So if it was actual open book, then you would have. Right. So if it was an actual open, or the union of inverses.
I'm losing you a little bit, Gordon, but
the sigma I right now.
Gordon, we're losing your audio.
Yeah, I'm cutting it off. Let me try and move a different room.
But the answer is yes. If it was an open book without any critical points, then those two surfaces would have the same genus.
Right. Let me see if I move over here, I get better connection.
So I'm going to call the lift of that H0, and then the inverse image of that arc is H pi minus epsilon.
And so this is sort of the standard thing where you have, I mean, you know, in a standard open book, if you do, you know, you get this Hayguard splitting Hayguard surface by taking two pages and joining together along the binding.
Yes.
But you're sort of going back and saying, well, wait a minute, suppose I had already done zero surgery. So now there are actually two fibers, two closed surface fibers of the thing. Now I can undo the zero surgery by puncturing every one along, you know, this closed orbit of this vibration. Then I get a hole in each one. Then I can take a connect sum. Then I do a connect sum that way. And I don't know if it somehow, like it, for me, I'm hung up on like, well, which way do I do the connect sum? Do I go around the top half of the circle or the bottom half? But it sort of doesn't matter.
You don't have to do the zero surgery and undo it. You can just see that there is this open book decomposition, and the binding is this ribbon disc, this ribbon disc D, or this handle ribbon disc. And it's weird because the D is contained.
Well, no, the binding, I mean, hold on. The binding is, I mean, on three-dimensionally, the binding is a one manifold. What do you mean by saying it's a ribbon disc?
Oh, there's a four-dimensional open book in the background as well. So I want to think of living above this.
Yeah, go ahead.
So living above this.
So the four-dimensional is by adding the I direction in this annulus.
Yeah, so you have this homotopy 4-ball B sub P, and I want to remove the disk D. And I can think of D as living in the same way I think of the three-dimensional binding as living as the boundary of each of these fibers. This D is a disk in the boundary of each